Okay, in this next part of the module, we're going to take a look at lines in space. So we're used to formulating and working with equations in a plane, right? Where we have x and y, and we have some line, right? Where we have its slope-intercept form to be this, right? Where b represents the y-intercept, and then m is the slope, right? And we characterize the slope as change in y over change in x. Excuse me. Okay, so we want to take this idea of a line and transfer it or find the equation in the three-dimensional space. All right, now things work a bit different, right? We call this a linear equation, right? Mainly because all our variables are to the power 1, and its resulting graph is a line, right? Now, if we look at our 3D grapher here, so what we have here is just two examples of equations that are in linear form, right? But linear in the sense, again, that all the powers of each of these variables are 1, right? But their graphs themselves, they're not lines. Their graphs are planes. And in fact, this turns out to be true for any linear equation in the 3D space with x, y, and z. The graph will always be a plane, right? So our formulation of a line needs to change, right? We could still write a line, right? And it turns out the way that we do that is through a parametric curve, right? So we need to parametrize it, and almost like we're doing like vectors. It's going to be a vector equation, right? The way you want to think of a line is just as a collection of points, and our equation is going to represent a vector that is essentially pointing to all those points that make up the line. All right. Now these concepts still kind of hold, but they're going to be different. They're going to be in one way to characterize a line. It's going to be a vector equation, right, with some parameter t. Right, so we're going to need, for this vector equation, we're going to need two things, right? We're going to need what's called a direction vector. So this kind of tells me it takes place of our slope, right? Instead of a slope, which is what we use in a two-dimensional plane, we have a direction vector. And that'll be multiplied by our parameter t, And then we're going to need some kind of initial point. Right, a point that is on the line. Right, now this direction vector does take the form of a slope, except here each one of the components represents a change in x, change in y, and a change in z. So it tells me as the parameter t changes, right, how does the x, y, and z component change, right? That's what these components tell me. And then the initial point is just the constants x1, y1, z1, right? These are all just points that are going to be on our line, right? And then there's going to be a formulation of our line, right? So an example, just kind of making one up here. We have r of t. Is going to be equal to, let's just make some numbers up, 1, 2, 3, right? That'll be our direction vector t plus some point on the graph, let's say -1, -1, -1. Okay. All right. So let's say here, now let's look at what that would look like, right? So we can see here, let's try to remember these commands here. I think I got it here, curve. Okay. So curve, and then here the expression, what did I write? And again here, putting it as one vector equation, we could see this will be, you can distribute the t, so we get t minus 1, 2t minus 1, 3t minus 1. All right, and if it represents a line, t can be any real number. So we just say t goes from -infinity to infinity. If we want to plot a line segment, then we restrict the values of t. But here, if we're just talking generally of a line, then we're dealing with just any values for t. So let's take a look at this, right? T minus 1. So we'll do minus 1, comma, t, 2t minus 1, and 3t minus 1, and then the parameters t, and we'll say negative 50 to 50. Okay. All right, and then you can see there, now we have a line in space. Okay. All right. Okay, so now we can see that it is possible, right? But we have to take a different approach. And that approach would be a parameterization of the line, right? Where we need two things, right? We need a direction vector, right? And we have a point. Okay, in the next few videos, we'll look at if we're given a direction vector, how to come up with the equations. And what if we're just given 2 points, how to come up with the equations there. Okay.